Welcome back to Calculus 1. In the previous lesson, we studied continuity and used one-sided limits to analyze endpoints, seams, and jumps. In this lesson, we will examine another type of limiting behavior, a function whose values increase or decrease without bound. We will learn how to determine whether the values approach positive or negative infinity, identify vertical asymptotes, and distinguish an asymptote from a removable whole. Let's get started. Here's what we will cover in this lesson. First, we will recognize limits that fail to approach a finite number because the function values grow without bound. Next, we will use signs to determine whether a quotient increases towards positive infinity or decreases towards negative infinity. We will then locate vertical asymptotes and distinguish them from wholes created by canceled factors. Here, the finite limit does not exist, but the function's unbounded behavior is orderly enough to describe. Until now, many of our limits failed because the two sides approached to different finite values. This example fails in a different way. Consider the function shown as the input approaches 3. From the left, the outputs are negative 20, negative 200, and negative 2000. They decrease rapidly without bound. From the right, begin with an input of 3.1, followed by 3.01, then 3.001. The corresponding outputs are positive 20, 200, and positive 2000. As inputs move closer to 3, the outputs increase without bound. The graph shows the same behavior. The left branch falls below every level, while the right branch rises above every level. The outputs never settle near a real number. Therefore, the finite two-sided limit does not exist. What we can describe precisely is the manner in which the function becomes unbounded. The notation at the top summarizes the two one-sided behaviors from the previous example. From the left, the function decreases without bound, so we describe the left-hand limit as negative infinity. From the right, the function increases without bound, so we describe the right-hand limit as positive infinity. We must read the equal sign carefully. It does not mean that infinity is an ordinary number reached by the function. It describes how the function values behave as the input approaches the point. In the real number sense, the finite limit does not exist. The infinity notation adds useful information by telling us whether the values increase or decrease without bound. Because infinity is not an ordinary number, we do not perform ordinary arithmetic with it. When the denominator of a quotient approaches 0, while the numerator approaches a non-zero value, two signs determine the direction. First, determine the sign of the numerator near the point. Because it approaches a non-zero number, it keeps that sign in a sufficiently small interval. Next, determine whether the denominator approaches 0 through positive values or negative values. This sign may be different on the two sides. Finally, divide the signs. Matching signs give positive infinity, while opposite signs give negative infinity. In the example at the bottom, the numerator approaches positive 5 and the numerator is a small positive number from the right. Therefore, the right-hand limit is positive infinity. Always analyze one side at a time. If the two sides have different behavior, there is no single two-sided answer. Let's compare the two examples on this slide. In part A, the numerator is positive and the denominator is squared. The denominator therefore remains positive on both sides while becoming extremely small. A positive number divided by a very small positive number becomes very large and positive. Both sides approach positive infinity, so the two-sided infinity limit statement is available. In part B, the numerator is positive, but the denominator changes sign at 4. From the left, the denominator is negative, so the left-hand limit is negative infinity. From the right, the denominator is positive, so the right-hand limit is positive infinity. Because the sides disagree, the two-sided limit does not exist. An even power keeps the denominator the same sign on both sides. An odd power allows the sign to change. Now let's apply the same sign analysis to 3 examples. In part A, the numerator approaches negative 5, while the square denominator remains positive on both sides. Opposite signs give negative infinity, so the two-sided limit is negative infinity. In part B, the numerator approaches negative 9 from negative 9. Now, from the left, the denominator is negative, so the quotient approaches positive infinity. From the right, the denominator is positive, so the quotient approaches negative infinity. The two-sided limit does not exist. In part C, we approach 0 from the right. The numerator approaches positive 7, and the sign is a small positive number. Therefore, the right-hand limit is positive infinity. If we approach from the left instead, sign would be negative, and the corresponding left-hand limit would be negative infinity. Every example follows the same process. Determine the numerator's sign, determine the denominator's sign on the relevant side, and then combine the signs. Now it's your turn. For each limit, decide whether the result is positive infinity, negative infinity, or whether the two sides disagree. For problems 1 and 2, you are analyzing the same function, however, from opposite sides of 2. Pay close attention to the sign of the denominator on each side. For problem 3, both sides are included. Determine the sign of the numerator near -1, and then consider what the squared denominator does. Pause the video now and work all 3 problems. Then continue when you are ready to check your answers. Let's check the answers. For problem 1, the numerator is positive and the denominator is a small positive number from the right. Therefore, the right-hand limit is positive infinity. For problem 2, the numerator remains positive, but the denominator is a small negative number from the left. Therefore, the left-hand limit is negative infinity. The first 2 problems involve the same function on opposite sides of 2. Because the one-sided limits disagree, we cannot give one two-sided result. For problem 3, the numerator approaches -5, while the square denominator remains positive on both sides. Therefore, both sides approach negative infinity, and the two-sided limit is negative infinity. Infinite limits are closely connected to vertical asymptotes. If a function approaches positive or negative infinity from either side of a point, the vertical line through that input is a vertical asymptote of the graph. Only one side is required. A graph may become unbounded on one side while approaching a finite value on the other, and the line is still a vertical asymptote. For the functions considered in this course, an asymptote often occurs when the denominator approaches 0, while the numerator approaches a non-zero value. We confirm the behavior by evaluating the appropriate one-sided limits. The secant graph illustrates this pattern. Secant has a vertical asymptote at every input where cosine equals 0. A function cannot be continuous at a vertical asymptote because continuity requires a finite limit. Let's identify the vertical asymptotes in these 3 examples. In part A, the denominator is 0 at -3, while the numerator remains non-zero. Therefore, there is one vertical asymptote at -3. In part B, factor the denominator. Its zeros are 2 and 3. And the numerator is non-zero at both points. Therefore, the graph has vertical asymptotes at 2 and 3. In part C, the denominator is cosine. Cosine equals 0 at infinitely many inputs, and the numerator is always 1. Therefore, secant has infinitely many vertical asymptotes, 1 at each 0 of cosine. The routine is consistent. Factor the denominator, locate its zeros, and check whether the numerator remains non-zero at each candidate. A 0 in the denominator does not automatically produce a vertical asymptote. If both the numerator and denominator become 0, we have the indeterminate form 0 over 0. That form alone does not tell us whether the graph has a hole or an asymptote. For a rational function, begin by factoring the numerator and denominator and canceling every common factor. Then examine the reduced expression. If the reduced denominator is still 0 while the reduced numerator is non-zero, the graph has a vertical asymptote. If the problematic factor was canceled and the reduced denominator is non-zero, the graph has a hole. In either case, the original function is undefined at the point. The key question is whether the nearby graph escapes without bound or merely skips one point. The common mistake is declaring an asymptote at every 0 of the original denominator. Always factor and cancel before deciding. Now let's apply that process to the rational function on this slide. F of x equals x squared plus 6 minus 6 divided by x squared minus 9. Factoring reveals a common factor in the numerator and denominator. After canceling, We examine the two excluded inputs separately. At -3, the cancel factor creates a removable hole. The limit there is 5/6, so the graph approaches the point with a height of 5/6. At +3, no factor cancels. The reduced numerator approaches +1, while the denominator approaches 0. From the left, the function approaches -infinity. From the right, it approaches +infinity. Therefore, the graph has one vertical asymptote at 3. The two zeros of the original denominator produce two different outcomes, one hole and one asymptote. We can combine an infinite limit with a finite limit under several carefully stated rules. Adding or subtracting a bounded quantity does not stop an unbounded function from growing without bound. Multiplying a finite positive number preserves the direction of the infinite limit. Multiplying by a finite negative number reverses the direction. Dividing a bounded quantity by something whose magnitude grows without bound produces a limit of 0. However, these rules do not cover every expression. Infinity minus infinity and 0 times infinity are indeterminate forms. They can produce different outcomes in different problems and must be analyzed case by case. The same principles apply to one-sided limits and to negative infinity, with the signs adjusted appropriately. Let's apply the combination rules to the four examples. In part A, a finite value is added to a term that approaches positive infinity. The sum, therefore, approaches positive infinity. In part B, the first factor approaches +1, and the second approaches positive infinity. Multiplying by a positive finite value preserves a direction, so the product approaches positive infinity. In part C, the numerator approaches +7, while the denominator grows without bound. A bounded quantity divided by an unbounded quantity approaches 0, so the limit is 0. In part D, the finite factor approaches -5, while the other factor approaches positive infinity. Multiplying by a negative value reverses the sign, so the product approaches negative infinity. In each case, we identify the applicable rule and then state the actual limiting behavior. Infinite limits can also describe real-world model. This function estimates the cost in thousands of dollars of removing a percentage of a contaminant from wastewater. Removing 50% costs $24,000. Removing 90% costs $216,000. Removing 99% costs $2,376,000. As the removal percentage approaches 100 from the left, the denominator approaches 0 through positive values, while the numerator approaches positive 2400. Consequently, the cost increases without bound. In the model, complete removal cannot be achieved at any finite cost. The vertical asymptote at 100% represents that practical limitation. Let's bring the main ideas together. An infinite limit describes a function whose values grow without bound. The infinity symbol names the direction of that behavior. It is not a finite value reached by the function. For a quotient, two signs determine the direction: the sign of the numerator near the point at the sign and the sign of the denominator on the side from which the input approaches. Zeros of the denominator are only candidates for vertical asymptotes. Factor and cancel first. A zero that remains in the reduced denominator gives an asymptote. When that reduced numerator is non-zero, while a cancel factor produces a hole. Infinite limits can be combined with finite limits under the stated rules, but indeterminate forms such as infinity minus infinity and 0 times infinity require separate analysis. That completes the chapter. Everything that follows, especially the derivative, is built on the limit ideas developed here. Thank you for watching. In this lesson, we described infinite limits, determined their direction using signs, identified vertical asymptotes, and distinguished asymptotes from removable holes. This concludes our study of limits in Chapter 1. I'll see you in the next lesson.